It'll be in this room, remember? So I'm going to make some code. It'll be in the midterm 2 review folder, even though this is a lecture. It'll just be there. And yeah, just got a bunch of stuff to say. Feel free to derail me at any point. And just like, I made some slides. I'm going to type a bunch of code. I guess because I won't be typing any code next time. Well, you'll be typing the code next time, so 2 lectures amount of code that I'll be typing today, maybe. So yeah, let's just talk about linked lists first. It's like the base of it all. We'll make some code to like build up a linked list. We'll add 1 to every node, and then we'll print it back out. Let's do that. So like my goal is make a list. 1, 2, 3, null marks the end. And then there's always a concept of like, usually keep track of your first node, your last node, and then you can iterate through it starting from first. And what I want to do is like add 1 to all those nodes. Make it 2, make it 3, make it 4. So iterate as well as do something. Let us do that. Oh goodness, this is not a good time for the GitHub to go down. All right. I will call this lists.cpp. So every list is made of nodes, as we know. Struct node. And every node, let's have it have integer data. And it's always node star next. Where's the next node? So your nodes are made on the heap. Let's make 3 of them. 1, 2, 3. And then the data, of course, for 1, at least at the start, is going to be 1. And then 2 and 3 are going to follow suit. And then 1, the thing that comes after 1 is 2. The thing that comes after 2 is 3. And the thing that comes after 3 is nobody. So we mark that with null, right? So yeah, those are those. Usually you keep track of the first pointer, first node in the list, last node of the list. So the first thing is the 1. The last thing is the 3. And yeah, so what I'd like to do is we just built up the list. We want to add 1 to every node. Let's do that. So I'm just going to iterate through the list starting from first. So I'm going to add 1 to every node. And feel free to stop me at any point if you have any questions about something. We can draw it. So I'm just going to iterate through. So, all right, for every node, start it, my node pointer n at the first thing, keep going while n's not null. That means I have a valid node to look at right now. And the way that I advance my node pointer is just give it the next thing, n equals n arrow next. So what I want to do at each n that I see, I would like to take the data of that node and kind of do a plus plus. Technically, that's correct. That would work. But just to spell it out, n data equals n data plus 1. So yeah, that's me adding 1 to every node in the list, and then I want to print it out too. Print out the list to show my hard work. So it's the same kind of loop, but instead of adding 1, messing with the data, I want to print the data of each node that I'm calling n. Let's do it all in one line with a space in between, and then we'll break the line at the end there. So yeah, there's a loop going through it. And adding 1 and printing it out. So it was 1, 2, 3. Now it's 2, 3, 4. Questions about that? Lists are not too bad now that we're good at trees, right? That's even worse. So that's good. Yeah, to remember the time complexities, there's this nice website called bigocheatsheet.com. It is a little off for certain things, so you do have to take it with a grain of salt. Remember the things we really talked about in this class. But we were working on singly linked lists here. It's a little small here. Singly linked lists. We're caring about the worst case in this class. It depends on what it's saying. So like, it depends on where you're deleting from. Depends on where you're inserting to. But most of these are correct, all right, for most data structures. So like inserting at the beginning or end of a linked list is constant time. So I guess that's what it meant. Constant time for insertion for sure. If you want to search for something, if you want to go find the node, you got to start from first, go to last, because you don't know where it is. You can't do binary search even if it's sorted. So it's correctly linear time for searching. But deletion, is not always constant for a single linked list. If you're deleting from the front, it's constant, but if you're deleting from the last, you got to find like the second to last node. Then it becomes linear time because you got to go from the start to that. Okay, so just keep that in mind. And lists are great at just adding stuff in the middle. They're a competitor to like vectors and arrays for that reason. If you want to add like 1.5 in between 1 and this was originally 1 and 2, you want to add a 1.5. Boop. It's very simple and easy, right? You just change that next pointer. Not there anymore, but now it's here. And now that goes there. So as long as you have a pointer to the node before you want to insert something, you can very easily insert something. Quite easy. To add to the last element, also very quick, right? You have your old last. Maybe this is now, it was 3, now it's 4. Let's add a 4 node again. And then you just chop it off, right? It's like this is the new last node, so its next is null. The old last's next goes there, and now last is this new thing. It's just like a few pointer manipulations, and you've just added a brand new thing. So as long as you got a pointer to the thing before you want to insert, you're golden, it's constant time, but you may have to search for that thing. So do remember your complexities, but that is lists in a nutshell. Yeah. All right. Yeah, I'm just gonna go kind of speedy. Got a lot of typing to do. The next topic I would like to talk about is templates. Why not? So, my goal is let's make a templated function that like doubles things. You can't call it double, I'll call it dub for short. Like adds a value, uses the plus operation to add a value to itself. And then it's like you can do that to any type that has the plus operation. So we'll make that happen. So remember, the whole point of templates is you've noticed that you're repeating yourself. You've noticed that you're repeating yourself. The code is the same, but the types are different. So like the minimum example that we use, that's a good one. Int x, int y. If you got templates, you can solve this problem. So like, all right, on ints, what's the minimum function? It's like, all right, if x is less than y, return x. That one's smaller. Else, either they're the same or y is smaller. In either case, you can just return y, and you'll be correct. Return y. So there it is. And so it works the same for doubles, it works the same for strings. Why you copy and paste? Let's make a templated minimum function. And so what we say is template. We declare a type level variable, class T, class whatever you want to call it here. Class C. Instead of returning an int, instead of int min, int x, int y, it's going to be t min. Whatever that variable was. T min, tx, ty, right? And then you do the same stuff. And it'll just copy and paste it for you when you use the right types. So this is quite cool. This is, you're declaring a new type variable. It's very powerful and interesting. So this is now a type level function, I guess. And I'll show you what I mean by that. You can go down this rabbit hole further in a upper division class. Function is very cool. And so kind of when you call min, if you want to call it in the full way, like I want min on ints now, this min, you say min with a type argument. You think of it that way? Does that make sense? Like it was a function that took a type. Made you another function. Now this is min specialized for ints. Now you can give it the 4 and 7 or whatever you want to call it with, and it would work. So yeah, it's kind of like this is an argument in a sense. This is a type parameter. You can give it a value. There's a type argument. Kind of cool to think about that way. So yeah, yeah. So let's let's make these examples, and then I'll read the rest of this slide. Let me move this a little bit closer to me. So the goal is to make a function can't be called double because double is taken in C++, so we'll call it dub for short. It's going to double some stuff. So like maybe we made one function called dub that took like an x value and it returns x plus x, and we noticed like I want a few things called dub that work in a similar manner. So instead of just calling it with an int, I want to be able to call it with a bunch of stuff. So 84, yes, that's correct. And so let's template this. Let's make this a templated version. Instead of just ins, let's have it work for anything that has a plus operation. Just like tdub, tx. And then, of course, we have to say that t is not a real type, it's a variable type. So it's template class t. Do that for it, please. And so now it's happy. But it doesn't have to just be t, it could be u. You could say, as long as you're consistent, that's just your variable type that you're using for the duration of that definition. That's lovely. So it's still going to work. C++ can infer that you're calling it with an int. Oh, the u must have been int. It's fine like that. But you could also spell it out. You can call it correctly in full with the type operation, the type as part of it explicitly. So we've got, let's call dub on doubles. Why not? 3.14. That will create a version on doubles that works properly. You can also do, plus still works on strings, right? So let's have that work for strings, like string type. But you can also have it infer that if you give it a string, it's kind of weird to call it because unfortunately in C++, when you use double quotes, it creates a C string secretly, a constant C string value. And so if you want an actual C++ string, you gotta like wrap it in the constructor maybe. That would work, and then it would just return to you an actual string. But one way or another, you can get a string, put it there. It'll figure out, oh yeah, you want to double on strings, and like it does the right things. It specializes itself. You got a million functions for the price of one. It's lovely. Infinitely many, really. Yeah, so that's templates. Templated function coming back to us. Make sense? We're pros. So yeah, let's make a class just to show you that you can do the same thing where you make a whole class that's specialized by some type, or it's generic in terms of some type that we don't really care about. It's just there. It's just there for us. So let's make a doubler class, a class that takes like a member variable, it holds on to that thing, and then it doubles it whenever you ask for that to happen. I think that would be a good silly example. So make a class called doubler. If I can spell doubler. And so the public things are, let's have it hold on to a member variable. It's just like, we'll be lazy. We'll make it some type of thing that we want to double t, and then a function called dub that's const, doesn't need to change our little member variable, that gives back that thing doubled so it's still a t. And so, yeah, let's have it be templated. Template, the whole class is templated now. T is a variable type. We hold on to a thing of type t, and we give back a double thing of type t whenever we ask for that method to be called. All right. So if we implement this method here outside, we got to tell it first that it's a method. So it is doubler's dub method, but that's not quite the end of the story. We also have to say that t is still a variable because this is a new place. We got to remind C++. This is still a variable type. And then also this doubler class, it's not doubler's dub, it's doubler on t's dub. Because you could, there's actually a way, if you really wanted to, just like, all right, if anybody makes a doubler on ints, this is the one I want to use. You can make it weird like that and give a different implementation if you need to, but that's beside the point. It's like doubler on t's, generic thing. What does the dub method do? It returns our x member variable doubled with a plus operation. So there's a templated class that does a silly thing. Do you see it? It's just like the class itself now is templated. So that involves member variables, a bunch of methods maybe, can use that variable type. Okay, and you can have multiple variable types. You can hold on to another thing, like a type u that's also there, whatever you need. And that's what we did for our hash maps, right? So we got all those. Yeah, let's make some doublers now. I'll make a doubler object, a doubler on ints, please. Call it d. Set the x to 42. See out d. Ask it to double itself. Yeah. And then you do the same thing for other types, like a doubler for doubles. Call it d2. d2's x is something that's actually a double. d2.dub. And so just like the whole class now is templated. That's not a big jump. And so it still works. Any questions about that? You see it? So you've done it enough by now, just making sure you remember it all. let's see here. So if we're good with templates, let's keep trucking. I just got a bunch of things. So, and then the rest of the time after all this is going to be yours to study and ask questions. So here, if we're good, let's go to stacks and queues and decks, because decks they're all similar, right? They're all linked lists at the back end. It's probably the most common way to want to do it. So let's make that happen. So first of all, let's draw them. A stack looks like this. It looks just like the function call stack, but you can hold just arbitrary values. Like you can push empty stack, you can push 3, you can push 4, you can push 5, and there's always a concept of where the top of the stack is. So here's the top of the stack right now. And you can pop your stack, and the popping happens from the top. Okay? So that means a stack is, it's called LIFO. It means that the last thing you put in is the first thing that comes out. Remember that? That's stack stuff. And you can represent a stack with a list. Usually that's what we're going to do. Stacks and queues and decks. So you could have stored this as a list 5, 4, 3. So I'm using the Python syntax now, but 5, then 4, then 3, those nodes in that order. And then when you pop or push, it's from the front. It's to the front. Okay? So you push to the front when you push to your stack, and then you pop from the front of your underlying list when you're popping from your stack. That's the window into the list you give to the user if they just want to stack. Okay? So there's that. Queues, and then yeah, stacks are LIFO. So you could have stored these in any order. You could have been like, all right, I'm pushing 1, then 2, then 3. 1, then 2, then 3 to my stack. And so here's the top. You could have done this in either way, but like you get better time complexity if you do it to the front. So top. This is, you could have pushed like 1, then the list looks like this. Oh, is there a question first?
For the stack, could you not push and pop from the back of the list?
You could, but that would be unfortunate for the running time. Because you remember to pop, if we're going to use a singly linked list like we learned in class, if you pop from the end of a list, you got to go and do a linear time search for the second to last thing. Yeah, good question. Does that make sense? Yeah. So I'll show you both ways. I'll draw you both ways right now, though. So like, let's say we do push back. If we push back to our stack or to our list to represent the stack, so you push the 1, then the 2, there it is, then the 3 node. It looks like that. When you pop, then you're popping from the back of your list, right? You're pushing to the back, which is constant, but you're popping from the back, which means you gotta go find that 2. You don't have an easy way to find it, especially if your list is very long. It's a linear time operation. So either way, like it could have been that, but I think we're going to prefer to do it with a push front, because then we can do a pop front, and that's easy. All right. So if it was to the front, then you push the 1, it's just the 1. You push the 2, now the 2's there in the list. You push the 3, now the 3's there in the list. And then it's a pop front to get rid of the top thing, which makes it easy on us. Constant time. And so stacks are LIFO. Last thing in is the first thing out. Last thing you put in, that 3 was the last thing you put in. That's the first thing that's going to be chopped off when we pop. Then the 2, then the 1. It's going to go in like reverse order. Remember, and that makes sense to us. So keep those terms in mind. Queues are kind of, I guess they're the opposite in a sense. So a queue has a concept of, you got the front of the queue and the back of the queue, or the rear of the queue, and you can put stuff in it. So there's always a front and a rear, front and a back. So let's say I push 1, 2, 3 to a queue. It will look like this. Then first there's a 1, then it goes 1, 2. If I push the 1, 2, and then it goes 1, 2, 3. When you push to a queue, you always add, like here's the front. You always add to the back, or the rear, however you want to call it. Some books say that. And so I guess it's a good thing to do. Again, you can use this as a list. I think it's probably worth it to turn this into the list 1, 2, 3. So you're pushing, when you push to a queue, push back. That's constant. And then when you pop from a queue, the difference from a stack, right, is that you're popping from the front. It's like the person who's been waiting the longest gets to be dealt with first. And so that's a push front. And so that's going to give you constant time, even for a linked list that's singly linked. And that's wonderful. So yeah, queues, opposite to stacks in a sense, they are FIFO. The first thing that you put into a queue is the first thing that you're going to pop off from it. It was just waiting so patiently. That 1 was the first thing we pushed, and so it's going to be the first thing that we take. All right? So it's good to use a list for those. But yeah, I think that's what I want to say. That gives us the best time complexities. Again, implementing using a linked list. If you use a doubly linked list, we don't have this problem, but we learned to implement singly linked lists in this class. But the time complexities are nice and constant if we do it in this way, at least. It's constant time to push, to look at the thing at the top, it's just like look at the thing at the front or back of your list, depending, and give it back as a copy or something. That's constant time. To pop, if we do the right ordering that we were talking about, then you're getting the nice pop front of the linked list, which is constant time no matter what you do. So yeah, that's these things, single linked lists. Do we have stacks and whatever on here? No. But they use lists, and you know now, all right? So yeah, are you ready for an example with code that involves, I guess, both a stack and a queue? All right. I'll just use the ones baked into C++. Make it easy on myself. So stacks and queues. So if I want to use stacks and queues, stack, queue, and I want to use a stack to reverse a vector. So just as a silly example, because you get things in reverse order with a stack. So let's get all those in there. So let's say I've got a vector. There it is, holds 1, 2, 3. I'd like to create a reversed version of that vector. So I'll start it empty. Reversed. Something like that. And okay, I want to use a stack to do the reversing, just as a good example. All right, so I'm going to make then a stack of ints that's initially empty. That's what the constructor does. And then I'm going to add every single element of v from left to right into that stack s. So for every int x and v, go and add it into the stack s. It's s.push that value. All right, so now the stack holds everybody in the vector. It was pushed in reverse order, so I pushed the 1, then the 2, then the 3. I've got exactly this going on, and you better believe that the first thing I'm getting off, because stacks are LIFO, I'm getting off the 3 first. So that's the reverse order thing. And so if I just continuously pop from this stack and push the thing that I'm popping, before I pop it, into the vector, I'm good. That'll give me reverse order. So for forever, while that stack is not empty, so while s.empty is false, I got a value at the top of it still. Go and get that thing. Go and get s.top and take it and put it at the end of this vector. Push it back to this vector that's meant to hold the reversed thing. So v reversed dot push back that value. Does that make sense? So there it is. It's in there. And then now I'm done with that thing at the top. I want to go on to the next thing, so I'm going to pop the stack. You got to do both separately for C++'s version. Sometimes pop in certain implementations gives you back the thing that just got popped as a copy, but for C++, you got to use top. All right, so there it is. And so once this is completed, the stack will be empty. This is now going to be false, which means the stack must be empty. And then v reverse will hold all the values in reverse order. So then I can go through that for every x and v reversed. Then let's see out those values. Make sure it worked. Nope. There we go. Cool. So there's like the relevant code, all of it. Boop. So there's a very complicated program to print 3, 2, 1. Any questions about what happened? See the use of a stack. Kind of gives you reversal because they're LIFO. The last thing in is the first thing that comes out. Yeah.
I think I've done the same for int x and s.
Can you iterate through a stack? That is something that it's a library decision. For the ADT for stacks that we talked about, that is not something that we're considering to be possible. Okay. So usually you interact with a stack through push and pop and top. But I think that maybe you get that in C++. I do not remember. But there might be an iterator. It just depends on if there's an iterator. Can we get the thing? It looks like no, they're not giving us an iterator. So we are forced to do the things in that way. That's a great question. But yeah, sometimes like I was thinking of deck maybe. The deck class in C++ specifically does give you an iterator. Or yeah, it gives you an iterator. It also lets you go to an arbitrary index of your deck, which you would think shouldn't really be possible because the deck operations that we talked about is like the front and the end you can interact with only. Yeah. So they're just being a little bit fancier because they can, but usually, traditionally, at least for stacks and decks, like the stack is you push pop, get the top. For decks, it's do stuff to the front and back only. For queues, it's push pop, get the front, stuff like that. But yeah, these are good ideas. It depends on your definition, I guess. Is the real answer. Yeah. Other questions? Keep them coming. All right, so that's the very philosophical answer, I guess. Let's see here. What was I doing? So those are stacks things. Let's do queue things. So let's do just an example of queue stuff. It's just like, what can you do to a queue? A normal queue, not a priority queue, which we know about now. It's like these things. See if it's empty, get its size, look at the front. This one lets you look at the back, which is maybe a little non-traditional as well. But they let you do that. You can push, you can pop, etc. So that's kind of what you want to be able to do to a queue. But when you interact with it, it's like you're pushing to the end, or you're popping from the front. It's FIFO. The first thing in was waiting so patiently. It's the first thing that comes off when you pop. It is like a line. So separation, queue stuff. So I'm going to make a queue of, let's do not ints for once. Let's do a queue of doubles. Call it queue, of course. And I want to push stuff. So push 4, push 5, push 6. Is that what I drew? No, I drew 1, 2, 3. But imagine I drew 1, 4, 5, 6. That's the order now. It goes in order. 4, 5, 6. 4 has been waiting the longest, so 4 is getting popped first. All right, so here's like the drawing in text form. 4, 5, 6. That is my queue right now. All right, where this is the front and this one is the back. Yeah, so there it is. And so if I want to iterate through this queue, I can. I'm going to get the things in the order in which they were pushed. So while, if I want to iterate, while queue.empty is false, while it's not true that the queue is empty, so while it's got stuff in it that I can look at, it's got a front now. It's got something concrete at the front. Go there. Queue.front, look at the thing, give it back as a copy, and then we'll print it out. And then that's me looking at the 4, and then the 5, and then the 6, in that order. And then once I'm done looking at it, I want to pop the queue so that I'm on to the next one, because you can only interact with it like the queue is this, I popped it, now it's just 5, 6. Now there's a new thing at the front that I can go and look at in the next round of the loop. So that's the point of that, and it's new line to break it. So this is just another complicated program that writes 4, 5, 6. Do we see how it's working and how it's different from a stack? So this was a stack, I would be getting the 6 off first, right? But it's not. I'm getting the thing that was waiting the longest, that 4 value, which is great. So patiently it was waiting for us. So yeah, I think that is most of what I wanted to say. So they are going to use linked lists. Decks use something weird that's kind of equivalent anyway. It doesn't really matter. But stacks and queues, you can think of them as using linked lists to implement stuff. And you can always look at like what is the complexity, like the queue push complexity. It is one call to push back on the underlying container, which I guess is handing off the problem to somebody else. But by default, that container is, oh, it's a deck. Interesting. Or for queues, you can change it, though. You can change it to a list of t's. Why not? But it would have been constant because lists, pushbacks are constant. Interesting. So yeah. Yeah, it lets you use this container. You could make your own, actually, because it's like it's going to use these things on it. Which is kind of cool. So you can make your own stuff as long as you use these names. That's kind of fun. So yeah, the standard container classes deck and list fulfill these requirements. So that's at least useful knowledge. All right. So it's using a deck, which is fun. It's like layers of complexity, but that's okay. So that's queues and that's stacks. I hope that makes sense. And then a deck is like a combination. It's like you get the front, you get the back. You can push the front, push the back, pop the front, pop the back. Get the value at the front, get the value at the back. It's kind of like a combination. All right. of the two at once. And I think I don't need to show you code of that one, though. I think we get it. Any questions about stacks or queues or decks?
Or decks, like over
Neither.
both.
Both, yeah. I would say both. I want to ask you that question about decks, because you can do either end. It's a double-ended queue. Let's see. Underlying, they use a weird kind of vector, but they could have used a doubly linked list. And so the way that you interact with it is you say which end you're going to. It's like, I want to push to the back, I want to push to the front, I want to pop from the back, I want to pop from the front. And I also can get the values. Give me the thing at the front, give me the thing at the back right now. Is it empty? Usually that's those are the default operations. Is it empty? What's the size of the thing? The rest has been added by the C++ people for convenience. But traditionally, that's kind of what a deck is. Front and back at the same time. So just like whatever order you care about. You can simulate FIFO or LIFO, I guess, if you just use one or the other. But you get the choice. Yeah. Other questions? All right, moving on then to hash tables. Sorry, the font is very small. There's a lot of stuff to say about a hash table. So we know that hash tables are cool but weird. I am not going to write any code about hash tables. I'm just going to draw pictures. So, okay. Running example. We got names of phone numbers. We got like a phone book. So you need to be able to take a string, right, and map an int. Those are the things. So it's always key value pairs, the things that we care about. So I would like to, in my hash table, I want to save the fact that my phone number, my name is a string. It maps to my phone number. There it is. And then if I want to add somebody else into the phone book, like it's another string. Some different string maps to a different value. So it's keys and values. There's a new key mapping to a new phone number. That's the value. All right. So like I want those things. I want to be able to insert those ideas in a hash table. And a hash table is just essentially a vector. It's just an array. It's just a lookup table. And so what is an array but a table where you access it with numbers as indices, right? That's how we use vectors. That's how we use vectors. If you think about it that way, like a hash table is just that. And so normally we just think of it as just like a bunch of things in order with indices. But those indices you can think of as keys, really. They're numbers. And so it's just like it takes numbers to some value, whatever kind of value you want to put there. For us, it's going to be integers. Those are the value types. And so we just need some way of like turning these into indices, right? Because the whole point is like I want to use a vector to store this stuff. So turn Lawton into an index where I can go looking for that string. So that's the job of hash functions, right? So like all these numbers, at the end of the day, they store things. I want some way of like taking my type T, that's my key type, like Lawton or mom strings, like whatever cloud of a type that is. We need some way of, some roundabout way of getting ourselves to a number for any type. For any type that we could use as a key. And that magical windy road is a hash function. Hash function, right? It takes the type of a hash function is it takes your type T that you're using for keys and it turns it into an unsigned int. Because that's a value that can then be shrunk down to become an index of our table, right? And so our hash table takes us there. Like maybe Lawton hashes to this index, and like that's where you go and you store your key value pair then. That would work, all right? So that's the goal. That's the job of a hash table, all right? And the goal as well of the hash table is to do this kind of key value pair stuff fast. We want to do it fast. So on average, for hash tables, every operation is going to be constant time. If you have a wide enough table, I believe that this is going to do that, right? Do we have hash table here? Hash table, cool. On average, yeah, constant time for search, insertion, deletion. Worst case time, things get disgusting. But average time we care about for hash tables. It's usually that. Got a big enough table, a good enough hash function. So yeah, if your hash function is horrible, you send everybody to the same index or something, or your table is so small that you collide all the time, then you gotta go searching for too long. Then it's a linear time operation. But on average, constant time, if you spread everybody out, you got like on average a constant number of things colliding at each index. So that's great. All right, so like unsigned int, your string could do some weird math to give back a giant value. You get back an unsigned int, that giant value is fine, you just shrink it down, right? You can always shrink down the result of a hash function to be an index of your lookup table. It could be anywhere, you just shrink it down using the mod size of the table usually. That'll work just fine, okay? So yeah, there's a couple competing ways because your hash function is never perfect unless you know the keys ahead of time. You usually don't. And so if you want to store something, you're going to store it as a key value pair. You save the key as well as the value, just in case you collided. You know what maps to what still. And then there's two competing main schools of thought on how to deal with collisions. You can either, just like every index of your table gets one key value pair, or it can hold multiple. That's the difference. So you still need to store the key and the value at the same time. So what we implemented was open hashing. We opened up the table. So at each index, we've opened it up. We've given a lot of room. Everybody can share. All right. You use a linked list or some other thing to resolve the things that clash. So for example, let's say that, I don't know, here's my hash table. It's a little small. I've got always integer indices of a vector. And at each index, we're going to use open hashing to map stuff. So let's say I want to insert Lawton mapping to my phone number. All right. So I'm going to hash Lawton. What index does that take me to by default? Maybe the hash function gives back some giant value. 1, 2, 3, 4, 5, 6, whatever. Then what you'll do is you'll do mod table size on that, right? To shrink it down to be a valid index. Mod table size. Something like that. All right, and maybe that gives you 42. And then you go to index 42 and you see, hey, what's there? 42. Is there anything useful there? You're going to have a list at every index. It's going to be a list. Maybe it's initially empty. This is the first thing that has been placed at index 42. If that's so, you will push back a key value pair for just me. L. Cool. There's my phone number and my name stored as a pair because you might have multiple things at that index. All right, that's open hashing in a nutshell. At each index, maybe a bunch of things mapped to like index 33. If you had a bunch of things there, like I insert, maybe that's where my mom's phone number goes. It's a little small, and then also my dad maps there or something. Like both of the phone numbers accidentally hashed to index 33 at the end of the day. Then you need the key value pairs because you're going to go looking at index 33 for both mom and dad when you look them up, right? By keys, you're getting back the value. You don't know which is which, so you got to save the key as well. Because otherwise you think the first thing could have been mom's number or dad's number. We have no clue. You got to save the key as well as the value. All right, so that's open hashing in a nutshell. You're going to use a list because there's going to be collisions. You would like a constant number of collisions to give you average constant time. But either way, you've resolved them that way. You're going to go searching at that index after you use your hash function on the key to go give the value back, update the value. You just go and find the key there. Get back the value or mess with it. Okay, so that's open hashing using lists. Questions about that? We have implemented it. We have struggled through that, I know. So good. Closed hashing is the other way of doing that. Closed hashing, I'll just show you a little bit. I'll use some drawings. Closed hashing is when we are stuck with just the indices of our table. Just the indices only. We can't store multiple things per index. We're just going to store key values at every index. And so that means if index 33 is taken by mom, and we're trying to insert dad, we got to go looking for another open index in some way starting from 33. Starting from that place that it initially took us to, our hash function. So closed hashing uses another index in the table to resolve collisions, and so it's always just like I'm trying to resolve collision. I am on attempt number I, starting at attempt 0 to insert something somewhere, and there's a bunch of different ways to go looking for the next index to insert something. So linear probing is the easiest one. So like, all right, if 33 is taken, if your hash function took an index 33 first, I is 0, right? That's the first thing you look at. Oh no, why are there underlines there? Go away. you just go to index 34 next, 35 next. Like each trial, you get farther away from where you started, but like that's the best you can do for linear probing, right? You stay kind of close still though. Like if mom is taken, it's using index 33, then we'll insert dad at index 34 if the hash function also took us there. So that's linear probing. Quadratic probing tries to jump around the table a little bit more. You have some constant values that create a quadratic function. It's always you start at the original index that your hash function took you to. Those like the I cancels all these out. Here, let me zoom in. The I cancels everybody out. Attempt number 0, just like go to the actual place. If that's taken, then this lets you jump around the table in a cool way that makes you like, go farther away, so that things don't cluster around a bunch of similar indices. That's helpful. So it lets you start jumping around the table a lot, and you'll just do mod table size, so you might wrap around as well, because these values get large, depending on what your C1 and C2 are. Then you're like squaring the I value, attempt number I, each time. So quadratic probing just lets you jump around a lot. And then double hashing is probably the best one, because it uses 2 hash functions. You use the first one, like the original one, the very first time, like, oh no, index 33 is taken. Then the second hash function starts coming into play. That's going to let you jump around. It's in a linear fashion this time, but it's going to be better than quadratic probing because you get a different way of jumping per value you're trying to insert, because your hash function for that value changes, doesn't it? Depends on the value now for that second hash function. It's not always a bunch of constants. It varies. I hope you see that. That's kind of why it's the best idea. So yeah, let me draw, I don't know. Let's draw a couple of these. So here, I have a hash table. Oh, let me zoom out. I have a hash table. Oh, help me out here. Yeah, thank you, PowerPoint. For once, I want this. There we go. I like this feature. Yeah, good enough. I have got a hash table. I've got indices. Indices are numbers. And then I'm storing key value pairs. I've got just the table itself to store stuff. All right, so let's say I've inserted my phone number and my mom's phone number, and the hash function for, let's see, the hash function for my number took me to index 42, because that's my key. My name is Lawton. We got there. 42 is the index we're being taken to, and like that one is open right now. All right, so every single strategy, go to where the hash function took you if you can. So that's like index 42. We're gonna place there the key value pair we're trying to insert. So we're gonna place Lawton and then my phone number 555 5555. Okay. And then the same for my mom. So I insert my mom's phone number. Maybe the hash function took us to index 33. So we'll go there. Not drawn to scale. Oh, goodness. Cool. So index 33 took us there. And then that one was open. So we stored the key value pair there. Mom. And then mom's phone number. Cool. So now let's look at all the options. So let's see. What shall I do? Let's just do linear probing first. Let's say that, I don't know, just for sake of example this time, let's say that I want to insert my dad's phone number. And so the hash function is going to collide with one of these. Let's say that inserting dad, I'm going to go use the hash function, h, on the key's value. So that, let's say that it gives me back 42, maybe after shrinking it. So I go and look at 42. Oh no, that's taken. I need to go somewhere else in the table now. I cannot reuse that index. So linear probing, which you can imagine is simple. Linear probing is like, all right, 42 plus, oh, we're on attempt 1 now. 43 is where I will try to place it next. And that one's open. All right, so linear probing would take me right next to this, 43. So 43 would put me there. That's where linear probing would insert dad. Just go to the next one. And I hope you see how the math checks out there. But if we were fancy, we could have done quadratic probing or double hashing. So let's say that, okay, we again collided at index 42. Can't use that one anymore. Let's find a new one with quadratic probing. All right? So with quadratic probing, you need to pick some constants that define a quadratic function. And everybody uses the same ones. Quadratic probing. Let's use constant 1 equals 3 and constant 2 equals something else. That is not a good 3. 3. Constant 2 is like 5. There are my values. And so the way that quadratic probing works is it's always just going to try this index next. So your trial is now, like trial 0 was everything canceled out. You went to the hash function index first. But now we're on trial 1. So we're going to do 42 plus the constant 1 times 1 plus the constant 2 times 1 squared because we're on trial number 1. That's the next place we go to. We're going to try index 42, which was what the hash function gave us back, plus constant 1 times our trial number plus constant 2 times our trial number squared, which is 42 plus 8, so 50. So index 50 is going to be where quadratic probing tries to place this thing. It's trying to spread it out. Just in case your hash function was kind of bad and it put a bunch of things, like the hash function gave you back a bunch of values within this range, quadratic probing is going to kind of be nice to you and spread more things out, even if that happens. So we're going to go to index 50 with quadratic probing next. And if that one was taken, you just put a 2 here, and that's the next one you try, right? It's going to jump you around. You might have to wrap around, okay? Let's do, that was 50. That's where quadratic probing would have tried to place the thing next, if it was open. But keep trying. That's where it would have gone. And then let's say that we were trying double hashing. So double hashing needs a second hash function, and then just like you go multiples of that given your trial number. So the very first time that you're on trial number 0, you use the original hash function to take yourself somewhere. 42, oh no, it was used. So I'll try 42 plus 1 times another hash function on that value, on dad. If that one was taken, I'll do 42 plus 2 times that hash function's value on dad. Okay? That's what will happen. So let's say I've got my second hash function. This is my original one. My second hash function on dad does something else. Let's say it gives back, I don't know, 37. I don't know. And let's pretend that, because we're going to have to wrap around, let's pretend that the table size, I don't know, let's pretend that the table size is 55, just for fun. All right? So what we're going to do is, all right, we're on trial number 1 now for double hashing. We've got 42. We're going to try index 42 plus 1 times. We're on trial number 1 now. We started at 0. Trial 1 times this 37. All right? So we're going to do 42 plus 1 times 37. And that's way too big if the table is 55 elements wide. Then we're going to do mod table size to bring us back down to a normal index again. And I did the math, apparently that's 24. Okay, so that's what we're going to try next. And we're just try multiples of 37 wrapping around our table if we need to. The next time would be 2 times 37, 3 times 37. Those are used. It's going to wrap us around and jump around in different ways depending on the value, because the 37 was dependent on dad. That's nice. That's why it's better than quadratic probing. This is always going to be the same amounts of wrapping around because these are constants for every value you're trying to insert. This is a different value per thing you're trying to insert because the hash function, in theory, will give you back a different value. That's great. Yeah, so that's that. So 24 would be not drawn to scale, but it would try to go up here, right? That's where double hashing would try to put the thing. Boop. Something like that. I think that's what I wanted to say. Are there any questions about any of this closed hashing business or any other hashing stuff? You see it? So I had you implement open hashing. I hope you see how much easier that is. I'll force you to do it in a different class if you take it with me. I think it's 26. But yeah, that's hash tables in a nutshell. We're almost there. So if we are still happy, I have, what next? Trees to talk about. Might as well. Linked lists. But you get two 2 pointers rather than 1, maybe 3 if you have a parent pointer, right? So, okay, we got trees. This is a generic tree, first of all. Let's talk about tree terminology before I go to code. So, okay, generic trees. Trees are made up of nodes. There's always a root of our tree. Edges separate nodes from their children and or parents. You have, yeah, this is a parent, and these are children. You can have like aunt and uncle relationships, sibling relationships. Nodes that have no children are called leaves, right? All these fun words that you remember. Arbitrary trees can have as many children as you like, so it's not just 2 pointers left and right. It could be like, it's like a vector of pointers essentially for generic trees, if you want to make one like that. But we just cared about binary trees in this class where you have two children at most. So the height of a tree is important. There's different levels, right, that you can be at. Level 0 is where the root lies. Only one node at level 0. Level 1 is all the root's children, root's grandchildren on level 1, at level 2, and so on and so forth. This is level 1, level 2, and then the max level that a node is at is your height. So this is, the height of this tree is 4. So how many edges can you get down to the lowest leaf? 1, 2, 3, 4. Okay. So that's a way to think about that. Yeah, there's a concept of smaller trees as well. Like here's a subtree. It's been drawn like that. This whole right side is a subtree. You just pretend it's rooted here. Give a pointer to that. Because that's how you represent a tree. You pass along a pointer to its root, and then you can, from there, fan out and get to anybody you want with enough pointer manipulation stuff, right? So yeah, that's kind of the goal. We've talked about binary trees though in this class. So like where you've got a root pointer and you're going to nodes that look like this, right? You've got only left and right to go down. So 1, maybe 2, 3, 4, 5. Something like that. So this is not a binary search tree. This is just a tree, okay? So yeah, let's maybe build that up in code because you could have disgusting things. But let's make, do I want to make that tree? Or do I want to make a different tree? Let's make this exact tree. Why not? I think that would be fun. So let's make this exact tree in code. Are you ready for that though? Does that make sense? What I want to do? So I'm going to turn this binary tree into a real tree in memory. So yeah, trees are made up of nodes. I would call them tree nodes. Every tree node has, we're going to store integers. So int data this time. And then just to make my life easier, we're going to do left and right pointers, but not a parent pointer. You could have a parent pointer. All right, so I'm going to make, I got 5. What's going on with my keyboard? I've got 5 nodes in this tree, so I'm going to make 5 tree nodes on the heap. I guess I'll call them 1 through 5. And then, yeah, let's set their data. So 1's data is 1. And then everybody else is as you would expect. And then, all right, who's where? So 1's the root. So the left of 1 is 2. The right of 1 is 3. So 1's left is 2. 1's right is 3. And then who else has children? 2 is the only other node that has children, right? So 2's left is 4. 2's right is 5. And then everybody else, 3, 4, and 5 are leaves, which means they have no children, and we mark that with null. So 3's left is the same as 3's right is the null pointer, and same for 4 and 5. Okay, so that's the tree, and then it's rooted at the 1 node, so if we want to pass that along to somebody, like the root of this tree is the 1 node, and that is that. So let's see, can I show you most of that? That's pretty much the game. Questions about that in memory? So yeah, for my first trick, let's just print out all the nodes. I'll show you, starting from the root. Let's say that the root is all we got. Let's get to the 1, print out the 1, the 2, the 3, the 4, the 5, and those are the data inside of those nodes. The data inside of those nodes, okay? So, starting from the root always. So the root is the 1, let's print out the 1 just by saying root's data, right? There's my 1. If I want the 2, that's root, go left, get the data, yeah? Root, go left, get the data. The 3 is root, go right, get the data. Are we following that? Does that make sense? Then the 4 is root, start the root, go left again, get the data. And then the last one is the 5 is start the root, go left, go right, get the data. And that is 5 lines, so that should do it. Oh, I did not mean to do that. There we go. Cool. 1 through 5, yay. Questions about any of that? See it? Not horrible. Let's see what else. We're gonna come back to some of these files. We'll come back to this file eventually and do recursive stuff. But let's talk about time complexity. So if a tree is nice and balanced, it's not swaying one way versus another. If your tree is balanced, like it's complete, remember those other terms, go look them up. I can't give you everything, but if they're balanced, we've done a proof to ourselves that the height is going to be proportional to log base 2 of the number of nodes. So that's really nice. It's as short as it could be, if that's true. All right, it's been spread out as much as possible, so the height is on the order of log base 2 of the number of nodes, and so that's not horrible. But just in general, you don't have maybe a balanced tree. Just like all of your operations are in terms of the height in the worst case, because that's how low down you need to get in the worst case to put something somewhere, right? You want to go searching for something, you want to go inserting something. Like it's always, you may have to get to here and go left or something. That's the lowest you could go. That's the height of your tree, all right? +1 maybe, all right? But that's still O of H. So remember all those time complexities. The website here, does it have trees just like normal trees? Binary search tree is close enough. So like in the worst case, they say linear rather than H for height, because they're just talking about numbers of nodes. And the reason they get that is because your tree could look like a linked list, could be disgusting, and the height is the number of nodes minus 1. That's horrible. But I think H is a better way to learn things first. You can deal with other things later. So yeah, it's like you want to insert, maybe you're inserting down here, and so you're going to follow a bunch of pointers to get there, and like that's the lowest you can go. It's the height of the tree that's getting you there, and then it's constant time once you're at the node. That is the parent. So just remember all those things. Yeah, you got those involved. Remember that you got traversals on trees, and they're going to visit every node, and so that's going to be linear time for those. But because you got to go to everybody and do constant work usually. If you're doing not just constant work, then of course you have to multiply. But in general, like you want to go print everybody out, you're going to everybody. It is recursive, but it still ends up being O of N. But yeah, to do one thing, like to do an insertion or something, maybe you're going down to the lowest level. It's the height of the tree. Okay, so that's tree stuff, just generic tree stuff. We know that we have a special kind of tree called a binary search tree, and there's plenty more to say about that. Are we ready for those? All right, so binary search tree stuff. Gosh, I guess I'll make some new code for that. And we'll go from there. But yeah, a binary search tree is a tree that has where every node exhibits the binary search tree property. So here's like the root. Let's say that this is my tree. Like 50 goes here. And then we have some very strong property. We have some strong ideas about binary search trees because every node obeys the BST property. All the values, and you go left, all the values are smaller than the parent. You go right, all the values are bigger than the parent, all the way down to leaves. It's true for everybody. It's a global property, all right? So you go left of 50, you can put 25 here, for example. You go right of 50, you can put 75 here. It's bigger. Everything to the right of this 50 should be bigger than 50. Everything to the left of 50 in this subtree should be smaller than 50. All right. Usually you don't have duplicates, but if you did, you just pick one side to be the less than or equal to, or greater than or equal to side. Okay. And then this is true for everybody. So if you go right from this 25, you cannot put 100 here. I hope you see that. It's bigger than 25, sure, but it's not smaller than 50. Everybody to the left of 50, all the way down to the leaves, better be smaller. I cannot put that there. Okay? That is how you have strong guarantees about where things can lie. So what's something that's smaller than 50 but bigger than 25? Like 33 could go here. Okay? And then smaller than 25 and smaller than 50, I could put 12 there maybe. All right? So that's the goal. There's a binary search tree. All right? So this is a property that is a global property. We're talking about subtrees, not just children. Everybody in the left subtree is bigger or smaller than 50. Excuse me. Everybody's smaller than 50, so that is that's quite strong, right? And everybody right here is bigger than 25, but also smaller than 50. All right, because of those ideas. Okay, so yeah, BSTs in a nutshell. Usually you can use them to create a map data structure with keys and values. So like you order the tree based on the keys, and then at each node you store values as well. If you have order involved, like you really want to print things out in order, you can do an in-order traversal of the BST. Do the key value pairs in that way. If you didn't want order, then it probably should have been a hash table because you get better time complexity that way. So yeah, let's do search. Let's do this code first. Let's make this tree. Let's do like a search function or something. And then we'll talk about stuff. Do I want to do other values? Not just yet. So, okay. I'm going to steal a lot of the tree stuff. BSTs. So I'll call it, I don't know, BST node. Why not? Just for fun. And it's made up of BST nodes now. And then if I would like to make this tree 50, 25, 75, 12, 30, I still have 1, 2, 3, 4, 5 nodes. So I can do most of this still the same. So I need 5 nodes. It's going to be, I can't call something 50 like that because that's a concept. I can say underscore 50. This is the 25 nodes, 75, 12, and 33. And then these are all BST nodes now. Yeah, and then it's like 50 is data is 50. Let me deal with that. 25's data. 75's data. 12 nodes data. 33 underscore 33 node data. 5, 12, 33. And then if I did this right, I can do this in the same kind of fashion. So like the left and right of 50 is 25 and 75. And then the left and right of 25 are 12 and 33. And then everybody else is null. 12, 33, and 75, those are our leaves, so they've got null. All right. 12 left and right are null. 33 and 75. So it's really just the same tree with new names, new values. And the root of our tree is the 50 node. Cool. Everybody else go away. So I've just done exactly the same thing as the tree example, just like they've changed the values and the names. So there's my BST now. It's got all these nodes in this order. The root is going and pointing to the 50 node. Let's make a search function that just like, I don't know, gives back true or false if the thing that we're searching for is there or not. So let's have it be able to be called like this. So give the tree and give what you want to search for in the tree. So see how the result of searching from the whole tree, starting at the root for 33, that should give back true because it's in the tree. And then maybe we could search for like 32. It's not there. So that can be a function. So bool, give back true or false if it's there or not. Starting from some tree rooted at root, search for a value called v. And the goal is to give back true or false if it's there or not. All right. So, okay. What I will do is I'm going to traverse the tree and go left or right, depending on what I'm looking for. So if it's 32 is the value that I'm looking for right now, or sorry, 33. That's the first one I search for. I'm going to start a pointer, right? I'm going to start an n pointer. I'll call it n. At the root, it's like, all right, I'm looking for 33. 50 is bigger, so I want to go in the smaller half. I want to go and say n equals n arrow left, right? Because if it's anywhere, it's got to be over here, because that's what it means to be a BST. And then, all right, it's bigger than 25, so I'll go right. N equals n arrow right. And that will place me, boop, right there. And then I'll find it. That's how it will work. So that's the goal. So so I'll start a node pointer at the root of the tree, and while that pointer is not equal to null, I've got something to look at still, and I'll see like what's there. So if the thing I see, or I guess if the value that I see is smaller than the node's data, 33 versus 50, for example, if the value I'm looking at, value I'm trying to search for is smaller than the data in the node, then I'm going to go left. It's like 33 versus 50, it's going to be in the smaller subtree. N equals n arrow left. So this is go left because v is smaller. And then the symmetric one is like if the value I'm searching for is bigger than the data I see, I go right. The value I'm looking for is bigger, so it better be in the right subtree if it's there at all. So like that's if I'm at the 25, I'm looking at 33. 33 is bigger than 25, so I gotta go right. It's gonna be over there if it's there at all. All right. But if none of these are true, it's not smaller, it's not bigger, it's just right, then we found it, right? Otherwise, return true. We found it. Yay. So that's how that works. So if you find it, you're going to stay within this loop and eventually return true. If we don't find it, we're going to break out of the loop. Just because we're going to hit null. If the value is 32, then we're going to get here again with our n. And it's like, oh, I will go left because 32 is smaller than 33. So I will go left and I will see nothing there at all. And then like n equals n arrow left gets me to null. Yeah, it gets me to null. And because of that, the next round, n is null, we'll break out of this loop. All right, just naturally. And so if we get here, it wasn't in the BST, so sad, we will return false. And so I'm searching for first 33, then 32. We're going to get true, then false. Oops, what have I done wrong? Node n was not declared in, oh, sorry, it's BST node. And I seg faulted. Great. Let's see what I was doing wrong here. Compare. At least we did true for this one. N data n equals n arrow right. I may have messed something up, but we can use GDB to figure this out. So the 75, these are all correctly leaves. I think I built the tree right, in theory. These all have the right data, but it looks like it went a little too far. Well, n is not equal to null. That's true. N equals n arrow right. Else return true. Yeah, I don't immediately see what I did wrong, so let's GDB it together. We got a dash G that. It looks like I copied my notes correctly, but who knows? What is the problem here? So we try to go right. We're looking at a node, print root. We're looking at the 50. We're trying to go right, and we got a seg fault? What? N equals n arrow right. Who? By who? N arrow data, n equals n arrow right. Does anybody see my error? Because I sure don't. And this is the second time we're going down this. Then I'll have to so v is 32, root is this. What's n? N is of course null. How do we get to null? n is not equal to null pointer. We should not have gone into the loop if n was null. Oh, I'm so sorry. Here. Else if.
Yeah, I get that.
Excuse me. There we go. That is so hard to find. All right, so happens to the best of us. So yeah, I was trying to, like, it did that one. I was like, oh, let me try again, just in case. I've already changed n. That was disgusting. I'm sorry about that. Sorry you had to witness that. There we go. True, false. So that goes to show. Good old if else, if else. Got to chain them together. So yeah, there's a search function. Any questions about that? GDB, when in doubt. All right, so time complexities we want to talk about. Yeah, if you want to search for something, you see that in the worst case, you're going down to the lowest leaf and maybe trying to go one more because the thing you're looking for wasn't even there. So you're going down the height of the tree, plus 1 even. So that's constant work per node. It's going to be O of H to do that searching. Insertion is exactly the same because, like, say you wanted to actually insert the 32, you'd again go searching for it. You go searching for it, you'd find the place where it's not, find that it's not there. It was supposed to be the left of the 33. And they're just like, there's your parent pointer, n is your parent pointer now. Go add it. New node, new BST node on the heap, set the data, set the parent pointers at the left of the parent. And it's all there, right? It's constant time to do the insertion once you put it there, once you find where it needs to go. So again, maybe you're inserting at the lowest level of the tree. So you're going down to the lowest leaf. So that's insertion. We know deletion is also O of H, right? Deletion is like you need a pointer to the node you want to delete. If you have that pointer already, it is constant time to chop off. Like if I have a pointer right there, I want to get rid of it, get rid of a leaf, easy. If I want to get rid of a one child case node, just do that. Do that for the parent, easy. Those are constant time things, but in general, maybe you have to search for the node first of all. There's O of H. Or if you're in the 2 children case, you know that you got to go find the predecessor or the successor, which is O of H in general. All right. So you're adding that along, and then you're getting to that. You're turning that into one of the constant cases. But you gotta go through that eventually. All right. So usually you're gonna end up searching for the node you want to delete. So deletion ends up being O of H in the worst case, even if you're not searching, because you hit the 2 children case a lot of the time. All right. That's the worst of the worst. Okay. So that's the time complexity, is the height of the tree to do pretty much everything. Does that make sense to us? Questions about that? So if you had a balanced BST, of course, like you had a red-black tree, AVL tree, then it becomes like the proportion. It's the height of the tree is proportional to proportionate to the log base 2 of the number of nodes, which is wonderful. All right, so you get logarithmic time for a binary search tree, which is binary search's running time. So it's kind of full circle at that point. So that's great. So yeah, I think that's everything I wanted to say about BSTs. Any questions about that before we move on to the last slide? Last slide of the review. Lots of talking and typing today for me. Last slide is about recursion. All right, so we know that you can find a smaller tree or a smaller list in a couple different ways. Let's do tree stuff first, because it's more recent in our mind. But let's say we've got, I don't know, this tree. This was our tree that we made in the tree file. It was 1, 2, 3, 4, 5. This was that tree. And so like here's the root. Do I want room for this? I cannot actually tell. Nope. Don't do that. There's my tree. Let's do a few things. So first of all, I've got a root. There's the root of my tree. You're passing along the whole tree eventually, like, and then you've got, like, say you want to search for some value again. So value, I don't know, is 4 that I want to search for. Got a value that I want to search for. What you can do if you want to search through a tree, that's just a generic tree. Just like recursively, if you think about this, well, you're going to recurse left and recurse right. You're going to go down this subtree and that subtree, and you get to let the recursion take over because this is the recursive case. You have things to go look through. So you let the recursion, you go look in this side of the tree to see if there's a 4 or not. it will give back true. You just get to assume it's going to do the right thing. That will give back true. It's search for it, it's there. All right. You also go down this half, go look for 4 in that half of the tree. It might also be there. I don't know. Give back false, right? You get to assume it's going to do the right thing. For your smaller subtrees, you're going to search for something. So searching gives back true or false if it's there or not. We're searching for 4, let's pretend. And then the one thing you do before you give back your final answer is maybe you were searching for 1. The one node that you've not yet considered was your roots node. So go look there too. And that is your recursive case. Recurse left, recurse right, look at your roots node, or them together, right? If it was anywhere as in one of those, yeah? That's going to end up being your recursive case. And then the base case can just be empty tree. Looking for something in an empty tree, it's never there. Something like that. So let's go back to the trees code and I'll show that to you. Boop. Cool. What do I want? Let's make a function down here, I guess, that searches for stuff. We'll do, so yeah, the result of searching this tree, starting from the root for the 4, for 4, for a 1, for like a 7, a bunch of values. The 7's not there. Okay, so that'll be how that one works. That will be my function. So, okay. I want to search just a generic tree. It could be to the left or to the right. So it's bool search, starting from some node that is the root of the current subtree I'm considering for some value v. See if v exists in the tree somewhere. All right. So base case, recursive case. If the root is null, that means we're trying to search for a value in the empty tree. That's a great base case because the value is never there, right? Base case, empty tree, v can't possibly be in there. So that's easy, return false. Otherwise, recursive case, we have a node to look at. All right, recursive case. We have a node, I don't know. If v is in this tree somewhere, rooted at root, it's either in the left subtree, in the right subtree, or it is the root itself's data. One of those 3 places. It's either to the left, to the right, or it's our roots data. All right, so let's try all those options. I can go and I can go searching through the left subtree. It's a smaller tree. Recursion guarantees that it will give me the right answer. If I go and I search root left for that same v, I will get a bool back, and I get to assume that that is a correct answer for was it in the small tree. Bool was it to the left. Equals that. Same for searching to the right. I'm guaranteed to be able to call it on the smaller tree, root right, that subtree, and I will correctly get back yes or no if it was there. All right? And I just need to build up the final answer correctly. So it's either to the left, to the right, somewhere there, or it's in the roots data. Was it the root? It's like, what was roots data equal to v? There. And so my final answer is, was it in any of those places? So I'm just searching to see if it was there at all. So return, like, was it to the left? Or with, was it to the right? If it's somewhere, it'll give back true. Was it the root? Does that make a little bit of sense? It's recursive, so it's a little melting your brain, I'm sure. But that's how it's going to work. And so we're going to get back true, true, false, because the 4 was there, the 1 was there, the 7 was not there. So that is recursive search. Questions about that? All right, I just got a bunch of examples. Let's do a recursive delete the entire tree. There's going to be an ordering issue here. So we've got a tree. We would like to delete that entire tree. I must redraw the tree. 1 small, though. 3, 4, 5. There's my tree. It's rooted here. If I would like to delete this tree, I gotta be careful. All right. I can't just like delete root and then delete root arrow left. Yeah. Because you've lost that pointer at that point. So the order should be recursively go down the left subtree to delete that tree, right? Just the recursion is guaranteed to do that right for you. Go down the left subtree. You assume that correctly deletes the left subtree of u in the recursive case. Then go down the right subtree. Assume that correctly deletes the right subtree of u. And then you're good to delete root from the heap. Does that make sense? Because then you've gone through all the pointers. It doesn't matter. And you delete it in that order. That is another recursive example. And so the order in which it gets deleted is going to be potentially a traversal order. See if you can figure out which one. So if I want to delete the tree, that's good because I'm not leaking in memory anymore from this program. I'll call delete tree on this entire tree rooted at root. And I'll spell it properly. It's going to be very similar to this code. I think you can imagine. I'll call it delete tree rooted here. There's the tree we're being passed. And then all this is going to be a little bit different. So, all right, base case, recursive case. In the base case, you got the empty tree. You're trying to delete all the nodes of an empty tree. There's nothing to do, right? Empty tree, nothing to delete. Recursive case, what we want to do is we want to recursively delete the left subtree, recursively delete the right subtree. Just let the recursion do it. Trust in it. Recursively delete the right subtree, and then we're good to delete our roots node because we're not needing to go down it at all anymore. Delete the root node. That's the last step. First, delete the left subtree, all of it. Delete the right subtree, let the recursion take over, and then delete the root node. And we'll print which node's data we're about to delete just for fun. So, all right, how do you recursively delete the left subtree? You say delete tree on root arrow left, right? That's passing along the left subtree for deletion, letting recursion take over. Just assume it happened, yeah? That's the magic of recursion. It really will work as long as you build everything else out properly. And you can prove that once you get to CSCI 26. Delete the right subtree, and then delete the root node. You just say delete root. There it is. It was on the heap. And just before that, though, we'll print out for fun. About to delete which node? About to delete the roots data, whatever that is, the 50 node. New line. Something like that. So there is my delete tree function. Do you see what it's doing? Do you see how it's going to delete the whole tree? So if you've done everybody else, your subtrees recursively, the last thing that you've not yet considered is you, yourself, the root. That'll do it. So, oh, sorry, it's not bool. It's going to be void. And you can see that it deletes in this order. It does the 4, then the 5, then the 2, then the 3, then the 1. Which traversal was that? I think I heard it was post-order traversal. So this is secretly doing a post-order traversal, and that's kind of forced upon you if you want to not dereference something you've just deleted off the heap. A pre-order would be a horrible idea. Because then you've deleted the root before you've gone down the subtrees. You can't even get those pointers anymore. Unless you save them, I guess. You save them in a temporary variable, that would work, I guess. But it would be extra work on you. So that's that one. And then, yeah, just remember your traversals in general. You got pre-order, in-order, post-order. It's just like, that's telling you in which order do you visit the root? Do you visit the left subtree recursively? Do you visit the right subtree recursively? This was a post-order. We'll do a pre-order for fun. I can do that. And remember that breadth first is not recursive. It uses a queue. It's like you have that gives you level order. In order, that will give you legitimately in this tree the 1, 2, 3, 4, 5, just like that, which is cool. Very neat. Yeah, let's do a pre-order traversal just for fun. Pre-order, these prefixes mean where is the root being looked at. Pre-order means root first, in order means root in the middle, post-order means root last. Subtrees around those, of course, recursively called doing things. Let's do pre-order. Pre-order, just to print it out, I guess. Starting from the root. So pre-order the whole tree, please. And that's going to be a void, I think. So pre-order traversal of this tree, let's just say when we visit a node, we'll print out its data. So pre-order traversal, dun dun dun. Don't want to do anything here at all. By the way, I left this empty. I could have just said return. Do nothing at all. Now it's not empty, but it still does nothing. Same thing. So you'll have this kind of same process here for pre-order. So you want to pre-order all the nodes in an empty tree? Nothing to do. No node to visit. Empty tree. Return. Do nothing. You could have added blank body. For pre-order, though, it's going to be root, left, right. So visit root. Visit left subtree recursively, because there's a lot of things down there maybe. Visit right subtree recursively. That's your order. So visiting root, we'll say that visiting means for us printing. It could be anything though. Maybe you're adding up all the values. I don't know. So there's that, and then visit left just means go pre-order the left. Pre-order that left subtree. Oops. Same for right. Pre-order the right subtree recursively. Let it happen. Let the recursion deal with it. As long as you've done everything else right, it really will give you that correct order. And so it looks like, you got to do the deletion last, of course. We get 1, 2, 4, 5, 3. And I hope you see that, because we're going down. This side first, pre-order is 1. You do the root, so here's like the output. You do the root, we output the 1, there it is, and then you do pre-order on the left, which is going to be root, left, right. So 2, 4, 5. And then it's time we did the root, we did the left recursively, now it's right recursively, there's just the 3 left, so it's going to be 3. That's why we see that order. Okay? So that's recursion on trees in a nutshell. Are there any questions about any of that? Stuff to study for sure. All right, I'm almost done talking. Let's do list recursion. It's honestly simpler. When you have a list, you do have a smaller list, just like you have a smaller tree to the left of you and to the right of you, but the list is just like there's one smaller list. It's just like the rest of the list. Like say here's your first node is pointing, your first pointer is pointing to the first node in your linked list. Like maybe it was 1, 2, 3. And that's it. You only have a smaller list in one direction, first of all. Like you can't just like circle this and that's a smaller list, because it's not a list anymore. A list has a null pointer as the last node. So the circled part could not be a smaller list. It's not actually a list in full. It's got to end with something. It did not end properly. So the way that you get a smaller list is like you're at first. There's the first thing in your list. Here it is. It's just like first's next. That's a pointer to the 2, which a pointer to a list node represents the rest of that list. So this is where you make your recursive call. There's your smaller list. You see it? Recursive call goes there. Oops, that's supposed to be a U. Recursive call happens there, and then like you let it do its job. Everything happens. It builds up the answer correctly, properly, and then the last thing that you have not yet considered, like you let it do the thing, whatever you're trying to do, like a search, for example. You search the rest of the list. It gives you back true or false if it was there or not. The one thing that you've not yet considered for the whole list is this node. You just need to go look at your first node now, because that's the one thing you haven't looked at yet. It's like the recursive call deals with the rest of the list. Then you just have to worry about the first node, the extra node that you haven't yet looked at. Worry about the extra node. Sorry, this is bad handwriting. Extra node. Eventually this will be legible. extra node. There. That's pretty much recursion on lists in a nutshell. Your first next gives you a smaller list. Then you just need to deal with that one extra node that you have not yet dealt with. Okay? So I've got a search and a deletion example, and it'll be very similar to trees. We'll watch it be very much the same. So I've got lists in this file. I have the list, I've forgotten. I've got the list 2, 3, 4 right now, don't I? Because I added 1 to all these things. So it's 2, 3, 4 on my list right now. And let's see. What do I want to do? Let's do some searching for searching the whole list, starting from the first node. You pass a list by passing the first node in it. You can get to every other node that way, just like you pass a tree by passing the root of that tree, because you can get to every other node through that. So first 3, let's search for 3, let's search for 4, those are in the list. Let's search for something that's not there anymore. The 1 is no longer there because we made it 2. That will be our recursive searching function. So bool search, starting from a list node now. Node first, what's the first thing on a list that we're currently considering? What's the value we're trying to search for? So this is recursively search through the list starting at first for v. So you can have base case, recursive case just the same as we did for the other, for the tree example. Just like your first could be null, which means you're being passed the empty list right now. You could have gotten down to that. You've got the empty list that you're trying to search for a value in. It's never there, right? Base case, easy base case, empty list. V can't possibly be here. Return false. So everybody see how that's a good base case? You'll get down to that. Otherwise, in the recursive case, you have a non-null node, so you can look at its data. You can look at its next. Recursive case, so either the value I'm looking for is in the smaller list, or it's in the node that's at me right now in the first element. So either V is in the rest of the list, which we can let the recursion handle, searching through all that, or it's in the first's data piece. So bool, was it in the rest, is just let search happen on first next. That's my smaller list. Search for the same value. That's gonna give, it's guaranteed the recursion will work because it's a smaller list I'm passing there. It's first next points to the 2 nodes, like everything else. For us, it's really a 3 node for the first call. Search for the same value. We get back true or false if it was there or not. Just let the recursion handle the whole rest of the list, even if there were 100 elements. It's fine. Get back true or false if it was there. The one other thing, it could have also been in our first data. That's the other place where it could be. So we need to look there as well. So was it in first, I guess? And that's just like, look at first's data. Was that equal to the V I'm searching for? And then my final answer was it anywhere at all? So was it in the rest, or was it in the first element? And there's your search. And it looks like we get true, true, false, which is what we were expecting, right? It's we were searching for, we had the list 2, 3, 4. We searched for 3 and 4, both there, and 1 was not there. So it's working, it's finding it. We're not finding it. Questions about this one? So it's similar? Excuse me, thank you. I just got one more then. I forget, let's do recursively delete a list. Just like get all the practice. We're doing the same thing in 2 different kinds of data structures. It's like we're getting some good practice there. So here. Dun, dun, dun. Is this the same though? Can I steal this from tree stuff? No, I'll just type it again, that's fine. So, all right, if I want to delete a list, should be the last thing I do, of course. Delete the whole list. Starting at the first node, that's how you get to the whole list, right? Starting at that node, go everywhere else. It'll be a void function. It'll still have the same base case and recursive case because like empty list, to delete it's quite easy, right? Delete list. Starting from that node. What do we get? So, okay, base case, recursive case, void this time though. So empty list, there are no nodes to delete. Just do nothing at all. You can say, just leave this empty body, or you can say return semicolon, because it's void. Otherwise, recursive case, that means we've got a node, at least one node to delete. This could be the last element for all I know, I'm not sure. But it has a rest that I can hand off to recursion. Let recursion deal with the smaller list, let it delete the smaller list, and then I just got this node left, right? Let it delete the smaller list, boop, imagine it's gone. Then all I need to do is delete my first node off the heap. I'm good to go. The whole list has been deleted at that point. So, recursive case, we have a smaller list. Even if it's empty, it's still smaller, right? To delete, that's on our first next, as well as first itself. So, gotta do this in the right order. Delete the smaller list so that you still have a pointer to that. Delete list, first next. There's the smaller list, I'm passing it. It's now deleted, and then we can delete our first node because I don't have to go through it anymore. So that's the proper order. All right. And for fun, we can print out what's about to be deleted. We can say cout about to delete the node with this data in it. And so there's delete list. I'm calling it on the whole list, which was 2, 3, 4. And it looks like, as you would expect, we do 4, then 3, then 2. The very last node gets deleted first. It's almost like a stack at that point. Cool. 4, 3, 2 in that order, but the recursion handles it all. If I ran this through Valgrind, I would get no leaks. All right. Any questions about the delete the whole list function? Because I think I'm finally done talking. Yeah, that was a bunch of stuff. Hopefully that was helpful. The code is in this folder, not a lecture folder. It's called Midterm 2 Review. I'll give that all to you. And of course, you get the recording too. But I think that's all that I wanted to say. Are there any last questions before I stop the recording? All right.